Before you ask me about the exam, I'm still working on the grades. I'm grading. I'm almost halfway through. So hopefully I will have the exams ready sometime this week. If you cannot wait until we meet again to see your grade, then send me an email and we can schedule an appointment. I can show you your exam in my office. Okay? Yes, sir.
I'll be great, but it won't happen.
So again, I'm halfway through, so for the first part and the first problem, I think most of you are doing well. Yeah, but I don't know if that's going to change for the last three problems. Okay? Any other questions? Okay, so here's the attendance sheet. And as I was telling one of the students, one of your classmates this morning, if you don't feel that you did very well on the exam, my experience with this class is that students tend to do better on the second and third exam, but you need to apply yourself. So if you don't understand some of the concepts for the first exam, you need to make sure that you understand them, because we're going to keep using those concepts from now on. Okay, so if you still have questions, you can always come to my office. We can go over your questions and we try to clarify your doubts. Okay? So again, it's very important for you to understand those concepts, because we're going to keep using them from now on. So for today, what we have is lecture in joint probability distributions. And this is material that is in chapter 3 of your textbook. So the agenda, before we go to the agenda, we're still on the second objective for this course, which is using probability models to describe uncertainty and to make decisions. Okay, so we're still dealing with probability models. You're going to go in a little bit in detail now in terms of how to define joint probability distributions, and also talk about specific probability models and probability distributions for both the discrete and the continuous case. Okay, so far, again, we started the class discussing some statistic measures. Then we moved to the probability side, and we talked about sample, event, counting sample points, the probability of an event. The last thing we did was to talk about random variables. And we'll repeat this concept over and over again. Random variables, because that's what we're going to be using most of the time from now on when we get in more detail about the probability distributions. So the last thing we did for the first exam was to describe what are probability distributions, and specifically the case in which you have discrete and continuous probability distributions. Today, we're going to go a little bit more depth here, and we're going to describe what are joint probability distributions for both the case of discrete and continuous random variables. So the agenda, again, in our last lecture, we covered these three first bullets. Today we're going to focus on the last bullet, which is the joint probability distributions. So the learning objectives: use joint probability mass functions to calculate probabilities. The second objective is to use joint probability density probability functions to calculate probabilities. Anyone remember what is the difference between these two? What is the difference between probability mass functions and probability density functions?
Is it one for discrete and one for continuous?
That's correct. And which one is for continuous?
Density.
Density functions, correct? So when we refer to probability mass functions, we are talking about discrete random variables, the ones that you can count. When we talk about probability density functions, we are talking about continuous random variables. Okay, so again, we're going to use joint probability mass functions to calculate probabilities. Same thing for joint probability density functions. And we're also going to calculate marginal and conditional probability distribution from joint probability distributions. So this is a concept that you already know, the conditional probability. This is a new concept, marginal. I'm going to explain what is a marginal distribution today. So let's start by discussing what is a joint probability distribution. And this is an example. So some random variables are not independent of each other and then tend to be related. So, for example, your vehicle speed and fuel consumption rates tend to vary inversely. So if you go at higher speed, you know that your fuel consumption is going to be higher. Okay, so also the length, if you consider the length as a random variable of an injection mold part, might not be independent of the width. And how many of you know what is an injection mold process machine? So basically what you do is that you push some material inside this mold and you try to compress that material to create a form. Okay, so that's injection molding. So the length of the injection mold part might not be independent of the width. Okay, so individual part might vary due to the random variation in the materials and pressure. So a joint probability distribution will describe the behavior of several random variables. In this case, we consider this example, the random variable x is the length and the random variable y is the width. Okay, so this joint probability distribution will describe the behavior of these two random variables together, which are not independent. Okay? So an example here, this is an example for your cell phone use. So you use your cell phone to check your airline reservation. I'm referring here to a system in which you need to speak to go to the next instruction on the system. So let's say you're calling this service system and you're going to request information about your reservation. So the airline system requires you to speak the name of your departure city to the voice recognition system. So now I have two random variables. Y, which you know the number of times that you have to state your departure city. So that's the number of times that you will repeat that information to your phone. And next is to denote the number of bars, signals, strength on your cell phone. So what we're assuming here is that the very reception you have, the very communication with the system you're going to have. So the number of times that you're going to repeat the information is less. So that's the information that we're presenting in this table. So basically what this table and the graph is also saying, we have the number of times city name is stated, so 1 to 4, and the number of bars that you have in your cell phone, from 1 to 3. So if you read this table, let's say you have a signal strength of 3 bars, then you have a higher probability of repeating your name or the city. You have a higher probability of repeating that name only once. Now, for the case in which you have only one signal, you'll see that the probability of repeating your name only once is very low, but the probability of repeating that name of the city is very high. Okay? So the very reception you have, the highest is the probability that you're going to repeat that state or city less times. And also you can see that from the graph here. So if you have, this is the number of bars from 1 to 3, and this is the number of times that you need to repeat the city, and this is the probability. When you go to the 3 bars, right here, the probability that you're going to repeat that city name once is very high. But if you move to 1 bar, then the probability of you're going to repeat that city name once is very low. So you see how those two random variables are not independent, because the information that you have about one affects the result of the other one. Okay? So that's a good example to represent two random variables that are not independent, and then you can create a joint probability distribution to describe their behavior. Okay? Any questions at this point? Okay. So let's look at the discrete case first. So let's say we still focusing on only two random variables, x and y, are two discrete random variables. The probability distribution for their simultaneous occurrence can be represented by a function of two variables, which are x and y. So now instead of having only the function in terms of x, we're going to have a function in terms of two variables, x and y. For any pair of values x and y within the range of the random variable x and y. So each variable can have an independent range. So x can go from 0 to 2 and y can go from 1 to 7, for example. Okay? So it is customary to refer to this function as the joint probability distribution of x and y. And for the discrete case, this is represented as f of x and y, which is equal to the probability that x equals a number and y equals another value. So it's the probability that those two events occurs at the same time. So for the example in which you have the number of bars and the number of cities, the number of times that you need to repeat the city name, this could be the number of bars equals 1, and the number of times that you need to repeat the city is 4. Okay, so you want to know what is the probability that those two events will happen. Okay, and you know they are not independent, so one will affect the other. That is, the values of this function give the probability that outcomes x and y occur at the same time. Okay, so now we have two random variables, and we want to know what is the probability that one event from one random variable and one event from the other random variable occur at the same time. Okay, so you're focusing on the discrete case first. So now we have the formal definition, and this is coming from your textbook. This is definition 3.8. So the function f, x, and y in a joint probability distribution or probability mass function. Again, we are dealing with discrete random variables first of the discrete random variables x and y if it satisfies these three conditions. So we solve these conditions for the case in which you have only one random variable. These are the same conditions, but now stated for two random variables. So the function evaluated in x and y should be always greater or equal to 0 for all the values of x and y. The summation of the probabilities for x and y should be equal to 1. And the probability of x equals a value and y equals another value is the function evaluated in those two values. Okay, and that's for a region that is described by the probability of x and y being within this sample space. Okay, so again, as you see, we are using the same concepts we learned for our first part of this course: random variables, sample space, event. So that's why it's very important for you to understand those concepts. Okay. So let's look at this example. So here we have two ballpoint pens that are selected at random from a box that contains three blue, 2 red pens, and 3 green pens. Okay. So this is a very simple example, but it will give us a lot of insight. Okay. So we have three different colors for these ballpoint pens. Okay, so we have the definition for a random variable x is the number of blue pens right here. And we have another random variable y, which is the number of red pens selected. Okay, so we are going to select 2 from this group that contains 3 blue, 2 reds, and 3 greens. And we have 2 random variables, one describing the number of blue pens and y describing the number of red pens. So let me put that here. So x is for blue and y is for red. And we need to pick 2 from the group of 8. Okay? So the first part of the question is asking for the joint probability function of these specific experiments. So now we need to describe a function for x and y, a joint probability density function, or probability mass function, because this is the discrete case. So the first thing that we need to do is to list what is our sample space. Okay? So our sample space is going to be based on our random variables, which are x and y. Again, x for the blue, y for the red. So the possible values or pairs x and y are 0, 0, 0, 1, 1, 0, 1, 1, 0, 2, and 2, 0. And why is that? Because from this experiment you're selecting 2 from this group, and these are the possible outcomes based on your random variables. So you can have 0 blue and 0 red from the group of 2. You can have 0 blue and 1 red. You can have 1 blue, 0 red, 1 blue, 1 red, 0 blue, 2 red, and 2 reds and 0 blue. Those are the only outcomes that you can have in this experiment. Okay, and that is based on your random variables. Again, you have 2 random variables, x and y. Is that clear? Okay. And also, we are basing our experiment of selecting 2 from the group. Okay. So, A, the total number of equally likely ways of selecting any 2 pens from A is. You now have to get the number of combinations, possible combinations from selecting 2 out of 8. That's a concept that we learned from our second lecture. You remember this and R? N factorial, R factorial, N minus R factorial. Okay, so that's the way that you can fit the number of combinations from selecting 2 or R from a group. So that is 8, which are selecting 2, and this is combinations, and this is theorem 2.6. So in this case, that will be 28. And again, this is for all the ballpoint pen. We're not only constraining our sample space to the blue and the red. This is for all the pens, 8 pens. Okay? So now, if we describe this function, f of 0 and 1, this means that you have 0 blue and 1 red, right? So f of 0 and 1 is the probability of selecting 1 blue and 1 red based on our definition for the random variables. First phase is for blue, second x is for blue, y is for red. Okay, so meaning that you have one green. So if your random variable is 0 and 1 and you're selecting 2, that means that you have 0 blue, 1 red, but that also means that you have 1 green. Right? Because you are selecting 2, and if you only one satisfy those random variables, that means that the other one is coming from the complement of the sample. Okay? So that means that you have another ball pen which is green. So the number of ways of selecting one red and one green is from the 2 reds you select 1, and from the 3 greens you select 1. So hence f of 0, 1 is going to be 2, 1 times 3, 1 divided by a 2. And this is equal to 6 over 28, which equals 3 over 40. Okay, so the probability will be given by the number of combinations for that event, F0 and 1, divided by the number of combinations for the experiment. Okay? And this is just for one case, F0, 1. We can compute this same probability for all the cases. And that's what I'm going to show you on the next slide. So if you look at the table, can I move to the next slide? Can I move to the next slide? Anybody? Okay. So if you look at this table, here we have f of x and y for the case in which x is 0 and y is 1. We have that the probability is 3 over 14. Okay, so if we repeat that process, the case that we discussed is this one. And again, this is for y equals 1 and x equals 0. If we repeat that process for the case in which you have 0 blue and 0 red, 0 blue and 0 red, then that probability will be equal to 3 over 28. Okay, same case, if you look at the case in which you have 2 blue and 2 red, that will be 0. And that makes sense because you're only selecting 2. So there's no way that you can have 2 of each. Okay? So we can create this type of table to show the probabilities for each outcome of the experiment. Okay? So the other question for the problem is to compute the probability of x and y being in this event or set, where A is the region, xy, where x plus y is less than or equal to 1. Okay, so in other words, what we are looking at is at the probability of having x plus y being less than or equal to 1. Okay, so now I want you to think about how would you compute that probability based on this. So you know x, you know y. You know what x means. X is the number of blue, y is the number of reds. So this is basically saying what is the probability that that summation 1001 is always less than or equal to 1. Will you be able to compute that probability with the information that we have here in the table? So if I tell you x equals 1, what does that mean? how many pens do you have of what type? One blue, right? If I tell you x, y equals 1, that means that you have one pen. Okay? So basically, what I'm asking is, what is the probability of those events that when you add those outcomes, it's always less than or equal to 1? You don't overthink it. It's very simple. You just have to look at the table and find those events or those probabilities for the outcomes that are less than or equal to 1. So for instance, that will be f of 0, 0, f of 0, 1, plus f of 1, 0. Okay, because when you add those variables or the outcomes of those random variables, this is less than or equal to 1, this is less than or equal to 1, and this is less than or equal to 1. So, meaning that we have, what is the probability of being 0, 0? 3 over 28, correct? What is the probability of 0 and 1? From the table, 0 and 1? 3, 14, correct? And the probability for 1, 0? 9, 20. So this will be equal to 9 over 40. And that's your probability. Does that make sense? Okay, so when you state that type of probability, again, you're dealing with random variables that are different, but if you have the information about the probability of each outcome, then you can compute such a probability. And again, this is for the discrete case. Any questions? Because now we're going to transition to the continuous case. So for the continuous case, again, if we deal with two random variables, x and y, the joint density function f of x and y is a surface lying above the xy plane, and the probability of x and y being in this set A is the probability that x and y is in the region A and is determined by the volume of f of x over the region A. So how many of you have seen double integrals at this point? Okay, good. So you know what the double integration means? So simple integration is the area under the curve. Double integration, you're looking at this area now. So we are going to be dealing with double integration in order to get that joint probability. So the function f of x and y is the joint density function of the continuous random variable x and y. Again, we have the conditions. As you remember, when we deal with continuous random variables, in order to get the probability, we need to do integration. So this also applies for the joint density functions for the continuous random variables. So again, we have the condition in which when you evaluate x and y, it has to be greater or equal to 0. And the double integration, or the probability of that joint density function, is always equal to 1. And if you want to find the probability to be on that set, then you need to integrate for that set with respect to x and y. Okay? So we are looking at the plane for x and y. Okay? So let's try to solve this problem based on those concepts. So again, now we are dealing with continuous random variables. And we're gonna try to apply those concepts for joint probability distributions, but for the continuous random variable. Okay, so this is an example in which we have a privately owned business which operates both a driving facility and a walking facility. On a selected random day, you let X and Y be the proportion of the time that the driving and the walking facility are used. Suppose that the joint density function for these random variables is given by this joint density function, in which you have f of x and y equals this for x between 0 and 1 and for y between 0 and 1. And then it's going to be 0 x elsewhere. The first thing that the problem asks you to do is to verify condition number 2 of definition. So this is the condition number 2, it's just this. So we need to verify that when you integrate for x and y, that integral equals 1, which means that the probability for that joint density function equals 1, and is based on the conditions for a joint density function. So let's work on that really quick. So we just need to check that condition 2 applies. So condition number 2 is just that the double integration from minus infinity to infinity for both variables f of x and y dx dy equals 1. Okay, so now let's try to describe those limits. So if you look at the limits for x, how would you define the limits for x? 0 and 1, that's correct. So 0 and 1, and then you have 0 and 1 for y as well. So our PDF or joint density function is 2/5 times 2x plus 3y, and we're gonna integrate with respect to x and with respect to y. Okay, so let's work on this really quick. So 0 and 1, the first integration equals 2x squared divided by 5 plus 6xy divided by 5. And this is evaluated from x equals 0 to 1 dy. So if you solve this, then you will get from 0 to 1, 2 over 5 plus 6 5y dy. But now we need to integrate with respect to y. Okay, so we solve the integration for x. You get a expression in terms of y. We need to integrate with respect to y now. So this will become 2y divided by 5 plus 3y squared divided by 5, evaluated from 0 to 1. And when you solve this, this equals 2 over 5 plus 3 over 5, which equals 1. So our joint density function satisfies the condition, or the second condition, for a joint density function based on our definition, because that integration with respect to your limits equals 1. Now let's look at the part B, which is more interesting. So part B is actually have question.
Oh, I don't know what is happening.
Yes. It will give you the same thing if you integrate with respect to y, but you need to make sure that you use the right limits. Okay? But yeah, it doesn't have to go that direction. You have to make sure that you're consistent with if you're integrated with respect to y, you're using the limits for y and then the limits for x. Okay? Okay, so I was not aware that some of you don't have the concept of double integration. Okay. So I'll try to, so essentially, if you know how to integrate, what you're doing is you're integrating again with respect to the other variable. But thank you for letting me know. So I take that into account. Okay, so let's look at part B. Part B is find the probability x and y are in this area, and this is the probability of being within 0 and x, 1/2, 1/4, y, 1/2. Okay, so that area is defined with the limits of 0 and 1/2 for x, and the limits 1/4 and 1/2 for y. So what we're going to do to compute that probability is to use our joint density function, and we need to integrate now with respect to x and y, taking into account the limits for each random variable. So that being said, the way you state this integration is the following. So the limits for x goes from 0 to 1/2, and the limits for y will go from 1/4 to 1/2. And our joint density function is 2/5 times 2x plus 3y dx dy. Any questions about how to state that integral? Okay. So again, if you use the integration with respect to x first, you need to provide the limit for x first. So if we solve this, this is going to be equal to 1/4, 1/2, 2x squared divided by 5 plus 6xy divided by 5. Evaluated from x0 to x1/2. So now you evaluate that integration, and you get a good expression or an integral in terms of y, which equals 1/4, 1/2, 1/10 plus 3y over 5 dy. And now you need to integrate but with respect to y. So in that case, this is y over 10 plus 3y squared divided by 10, evaluated from 1/4 to 1/2. So this will become 1/10, 1/2 plus 3/4 minus 1/4 plus 3/16, and that is equal to 13/160. Okay, so again, at this point in this class specifically, and for the purpose of the exam, if you state the integration, that will tell me that you understand the concepts of how to compute the probability. Okay, So that should be enough in order for me to understand that you understand the concept. If you're not able to get to the actual solution, then that's okay, because I understand that some of you don't have the course. Okay, but it's very important for you to know how to express this integration. Okay, because that's how you compute the probability. Okay, so we have seen two cases now. The discrete case for joint mass functions or distribution functions, and the continuous case for joint density functions. Now, let's talk a little bit about a new concept, which are marginal distributions. Okay, and we're going to have a lab today that is focusing on this concept specifically. So pay attention and you'll be able to get those words. Okay. So given the joint probability function or distribution, f, in terms of x and y, of discrete random variable x and y, the probability distribution only for x, that we're going to call g of x, of that random variable x alone, is obtained by summing the joint distribution function over the values of y. So if you sum the probability of the outcomes in terms of y, then what I'm saying is you're going to get the marginal distribution of x. And it will become clear with the example. Okay? Similarly, the probability distribution of h of y, which is our second random variable, alone is obtained by summing the joint density function over the values of x. Okay? We define g of x and h of y to be the marginal distribution of x and y respectively. Now, when we have continuous random variables, then the summations are replaced by the integral, which is what we have been doing so far. We're studying the concept for continuous random variables. We know that instead of summation, we need to use integration. Okay? So now we're going to focus on, based on the joint distribution that considers both random variables, x and y, how to obtain the probability distribution for only one of the variables, x or y. So you're going backwards, I would say. You have the joint. I want to know what is the probability for x, and want to know the probability for y. And that's a concept for marginal. Okay? So the marginal distribution for each random variable formed by summing the joint probability mass function over the other variable. Okay? So if we look at this example one more time, for the number of times you need to repeat the city name based on the reception that you have. If we look at the marginal distribution for 1, when x equals 1, then you're going to sum x equals 1 along the values of y. And that will give you for f of x equals 1, the marginal distribution, which is 0.20. Same thing for 2. If you sum along the y, you will get the marginal for f equals 2. F of x equals 2. Which means that the probability for this case, in which you have 2 bars, is 0.25. Again, we are not talking about having 2 bars and repeating the name 3 times. We're just talking about the random variable for x, which is the number of bars. So what is the probability of having 2 bars? It will be 0.25. What is the probability of having 3 bars? 0.55. What is the probability of having 1 bar? 0.20. And when you sum those probabilities, that should be equal to 1. Same thing for the y. What is the probability of you have to repeat the c 2 times? That will be the summation along x. That's 0.25. Again, we are not looking at the interaction of the variables. We are focusing only on one of them. Okay? So that's the concept of the marginal distribution. So we have the joint, We want to know the probability of x or y. So the definition, formal definition for the marginal distribution of x alone and y alone is given by, for a discrete case, is the summation for the x, g of x, for the marginal distribution of x, is the summation with respect to y of the joint distribution. For the marginal of y is the summation in terms of x of the marginal of the joint distribution. Okay? When you look at the continuous case, then instead of the summation, you need to use integration. So you're going to integrate with respect to y if you're going to get the marginal distribution for x, and you're going to integrate with respect to x if you want to get the marginal distribution in terms of y. Any questions up to this point? Okay, good. So again, looking at the same example, just want to make this concept very clear. If I ask you to show that the column and row totals in table 3.1 give the marginal distribution of x alone and y alone, this is what it just explained. So we know that the marginal distribution of x is given by the summation of, in terms of y, of f of xy, which is the joint. So if we want to find the marginal of x, let's say for 1, then what you need to do is to look at f of 1, 0 plus f of 1, 1 plus f of 1, 2. And that will be equal to 9 over 28 plus 3 over 14 plus 0. And that is 15 over 28. Now, if you want to find for h of y, this is the summation with respect to x of the joint. Let's say I want to compute h of 2. What are the outcomes that you need to consider in terms of f? You need f of 0, 2. Again, you're summing with respect to x. So you're summing with respect to x, you're expecting to see this number incrementing. So you go f02 plus f12 plus f22. Okay? So in that case, that will be 1 over 28. Okay, so this is the same thing I repeated. Just wanted to show you with the formula and with the formal use of the function. That makes sense? We're going to look at the continuous case now. Can I move to the next slide? Okay. Let's look at this example is asking to find g of x. So when you see g of x, you know what we are looking for, right? It's the marginal distribution of x. H of y is the marginal distribution of y. Okay? So find here g of x and h of y for the joint density function. So we have the joint density function. So let's start by defining g of x. So based on our definition, that is equal to the integration from minus infinity to infinity of x y dy. And this is coming from the formal definition right here. So the marginal of x is the integration with respect to y from minus infinity to infinity. If you compute the y, the marginal of y is the same integration but with respect to x. Okay, so let's look at this case. So in this case, if you integrate, what will be the limits for this integral? So we are integrating with respect to y. Okay, so that's correct. It will go from 0 to 1. 2 over 5, which is our joint, 2x plus 3y with respect to y. Okay, so if we solve this, this is 2 over 5, 2xy plus 3 over 2, y2, from y0 to y1, and this is going to be equal to 4xy over 5, 3 over 5, y squared, y equals 1, y equals 0. So this is 4x plus 3 divided by 5, 4x within 0 and 1. So your marginal distribution for x, your g of x, is this expression. Okay, so if you plug any of these values into this function, it will give you the probability of x. Okay, any questions? Now I want you to work in teams of 2 or 3 to find the marginal of y. Okay, so the marginal of y is in this joint distribution, and you need to fit with the result of the integration. This is just single integration, so I guess you will be able to solve. And I'll give you 5 minutes. Take a look. It's working here. Okay. So now you're interested on h of y. So you need to integrate. This is just the definition, f of x on y dx. So in this case, it will be from 0 to 1, 2 over 5, 2 times x plus 3y with respect to x. Okay, so that's the only difference in terms of the integration. So now instead of integrating with respect to y, you're integrating with respect to x. Okay, so if we solve this, this is equal to 2 over 5 times 2x squared divided by 2 plus 3xy evaluated in x equals 0 to x equals 1. So this becomes 2 over 5 x squared plus 6xy divided by 5 and this is equal to 2 over 5 plus 6y over 5, and this is for y between 0 and 1. Any questions? How many of you got it? Good. It's good. If you still don't understand the concept, please let me know. I'll go over the details, okay, with you. But again, the most important thing is if you're dealing with the joint density function and you want to compute the marginal, you need to be sure that you, if you're looking at the marginal for x, you need to integrate with respect to y. Same thing for a discrete random variable, you need to sum along the x variable, y variables, I'm sorry. And when you're looking for the marginal in terms, the marginal of y, then you need to integrate with respect to x. Okay? Now, you remember the conditional concept, the conditional distribution concept? Let's talk a little bit about that. So, for joint probability distributions, then we can also have joint conditional probability distributions. And the value of x of the random variable x represents an event that is a subset of the sample space, right? If we use the definition of the conditional probability as stated in lecture 5, then we remember that the probability of B given A equals the intersection divided by the probability of A. Okay? And we know that that probability for A needs to be greater than 0. Our A and B are now the events defined by the probability of x being equal to a particular value. So again, referring to the example of the box and the number of times that you need to repeat the city, x could be equal to the number of bars, so that could be 2, and y, the number of times that you need to repeat the name of the city, that could be 1. So you want to know what is the probability of those two events, given that you know the probability of one of them. Okay? So, in that same line, then if you state the conditional probability of y equals a value of y, given that you know the value of x, this is the same expression, but now you're going to have the joint density function or the joint probability distribution as your numerator and the marginal of this random variable as your denominator. Okay? So the intersection is now represented by the joint density function or the joint probability distribution. Okay? Where x and y are discrete random variables. Now, if we look at the formal definition, then we can express the conditional probability for both x and y. Okay, so if you're the conditional distribution of the random variable y given x is when you use your marginal distribution for x as your denominator. In the conditional distribution of x given y, then you use the marginal distribution of y as your denominator. Okay, so same concepts, now we're going to use them for our joint density and our joint probability distribution. Okay, so if we wish to find the probability that the discrete random variable x falls between a and b, when it's known that discrete random variable y equals a value, we evaluate this probability. So it's the probability of x being within these two numbers, given that y has this value. And then we're going to look at the summation of x between a and b using the conditional probability, where the summation extends over the values of x between a and b, and when x and y are continuous, we evaluate instead of using the summation, we use the integration. And this is going to become more clear with the example. So let me show you this example. And I think this is the last thing we're going to do today. the joint density function for the random variable x, y, where x is the unit temperature change and y is the proportion of a spectrum chip that a certain atomic particle produce, is given by this joint density function. Okay, so we are looking at the continuous random variable. These are joint density function. First thing that you need to do is to find the marginal densities and the conditional density for f of y given x. So as you saw in the definition, for you to find the conditional probability, you need to have the expression for the marginal, at least for one of the variables. Okay? Because if you look at the definition here, the denominator is always one marginal distribution. Okay, so you need to know what is the marginal for one of the variables. So let's find those marginal distributions. So g of x for this problem is the integration. What will be the limits for this case? And we know that the function is 10xy squared. And we're going to be integrating for y. But what are the limits? So with respect to y has two limits, x and y. Okay? So make sure that you follow the limits that are provided for the function. So in this case, instead of being 0, you will go from x to 1. Okay? So if you solve this, this is 10xy cubed divided by 3, evaluated from y equals x and y equals 1. If you solve this, this is 10 times x, 1 minus x cubed, for x between 0 and 1. Now we can find the marginal for y. Same thing, but in this case, what are the limits? Again, we have 10xy squared dx. So now we are integrating with respect to x. So what will be those limits? Correct. So you'll go from 0 to 1. And if you solve this, this is 5x squared y squared divided by nothing. This is for x equals y, x equals 0. So this is 5y over 4 for y between 0 and 1. And now we need to find the conditional probability, which you think is going to be easy to compute. So in this case is the conditional probability for y given x. So how do you find the conditional? You have the joint divided by the marginal of x. Do we have that information? Yes, we do. We know what is the joint. It's provided by the problem. And we have the marginal. So joint is 10 xy squared divided by the marginal, which is 10 times x, 1 minus x cubed. So our joint, or our conditional probability is 3y minus, and this is for x, y, y. Yes, 1 second. So So let me go from here to the, okay, so we have 10, do you know what this is coming from? 10xy squared, right? This is the joint, and this is the marginal for x. So we can take this, take this, take this, and take this. This is y2 divided by, yeah, you're right. Sorry, my math, it's not right at that point. Yeah, but this is the right answer. Any questions? We have a second part of this problem, and I think we can do that really quick. The second part is find the probability that the spectrum shifts more than half of the total observations, given that the temperature is increased by 0.25. Okay, so we have some information that is given, 0.25 units of the temperature, and we want to find the probability of that the spectrum shift more than half of the total is, what is that probability? So if you express that in terms of a math expression, then what we have is the probability of y being greater than 1/2, given that x equals 0.25. Okay, we solve this, then you need to integrate from 1/2 to 1 f of y, given that x equals 0.25 dy. So we have the integration of 1/2 up to 1 of y to 1 minus x cubed, which is our joint. Our conditional probability, if we solve this, this is 8/9. Okay, so we're gonna come back to this in our next lecture. But again, try to review, go back, try to understand the concept. If you still have questions, please send me an email and we can schedule a time for a meeting, or you can come to my office hours. Today I have office hours from 3 to 5. Not for this, not yet. Any other questions? Okay, so I'll see you next week.
Squared over 1 minus x cubed because you forgot that 3 up here. Yeah, like you forgot to bring in the 3.